About 10 minutes of discussion prior to the lunch break, so if we could get all our speakers to head up here and think of your questions. Think back to all this wide variety of talks here. Who would like to start?
A question about for Lin Hao about birth spins. So if birth spins are low, what is your thinking about the very high black hole spins in wind-fed high-mass X-ray binaries, where accretion hasn't really occurred, significant accretion has not occurred?
If birth spins are high, what are you thinking about LIGO black holes that are not spinning?
We have, with a paper led by Monica Gallegos Garcia, has shown that the X-ray binaries that we're seeing, they're going to go into KSA mass transfer. They're very tight orbits. And those KSA mass transfer X-ray binaries are not forming LIGO black holes. So you can have, I can't go into the details in 30 seconds, but I'm happy to point out the paper, but there's a long discussion and calculations about how basically the three high-mass X-ray binaries wind-fed do not become LIGO binaries. And therefore, and there is also another in there for why what becomes LIGO black holes starts with lower spins. Okay.
Yeah, so I guess it's probably more related to accretion, mass transfer types physics other than internal angular momentum transport, right? In that sense. I feel like this is very hard to look into. I mean, unless we have more observational evidence from massive stars about their internal rotational profile. Otherwise, very, very hard to say which one is true or not, or whether in some cases they're true, right? So I don't know, but that's my thought. Thank you.
Hi, Cheyenne Sharia. I have a question for Fulia. What prescription do you use for the angular momentum loss due to the gas around the binary black holes?
In our CMC models, or?
Yeah, so you have the binary black holes, both of the accretion disks, and are losing angular momentum due to drag.
Right.
Presumably, what prescription?
We don't do any evolution of these systems in CMC, but in our hydro simulations, we showed that significant fraction of the gas can be lost from the system. Is that what does that answer your question?
Okay, I thought that you had them into for a given binary black hole, you had some prescription for orbital decay. But you just did an example hydrodynamical simulation for one example system.
Exactly.
Okay.
Okay, so I would have a follow-up question on this one here. So what is the amount of mass that actually ends up in the mini-disk? Because I think normally you say that to change the spin of the black holes, you almost have to double their mass. So is that happening in these simulations that you're looking at?
Yeah, so these black holes don't have any spins initially, and in these accretion disks, when they are accreted by the black hole, they will give them spins, and these values are expected to be low because most of the mass can be ejected from the system. So we don't expect very high chi-effective values from even if they're aligned because of low spin magnitudes. Yeah.
So here you just showed one example from your simulations, but if you sample from the interactions that you get from the simulations you made, what are the typical mass in terms of this, like the mass ratios of the star coming in relative to the mass of the binary black hole? Is it that the mass of the star is always lower than the mass of the black hole? Is it the other way around?
That's a great point. So in our current models, we see most of the binary black holes interact with low mass stars because there is a delay time for these black holes, binary black holes to form. And by that time, massive stars expire. But in some cases, if we have some sort of primordial mass segregation where we don't need to segregate these black holes to the core and then form binaries, in those cases, or we can have primordial binary black holes that are already there, so potentially we can collide them with massive stars. So yeah, it's really uncertain currently what will be the final Chi-effective spin distributions given the different stellar masses they can interact with. But that's a maybe.
No, it's very interesting. Let us talk more about it.
Yeah, thanks.
Yes, I actually had a question for you as well. So just following up on Jochen's question, if you, how much mass can you actually keep on the black hole or on the binary, right? Because the sort of naive calculation suggests that if you have this stellar tidal disruption by a black hole, then accreting, 0.1 or 0.01% of the mass releases enough energy to unbind all the rest of it, right? So is that what you see in your simulations, or do you actually manage to keep more mass around?
So we don't do this regime because we need to do some GRMHD simulations to know exactly what fraction is lost versus accreted. But we're interested in cases where the star is more massive than the black hole. In that case, the regime is very different. Instead of forming a thin disk, we actually have a black hole sitting at the center of a star, like a quasi-star scenario. In that case, there is a very dense stellar spherical environment around the black hole, and it's very uncertain like what fraction can be escaped or not. And as far as I know, there is no any even GRMHD simulation look into this. So yeah, it's very uncertain.
Yeah, I had a question for Sylvia. I guess, have you looked at whether the rates of 2311, 23-like systems you predict would match the rate of this? And is there any way to also then predict what fraction of the rest of the population would come from chemically homogeneous evolution?
Yeah, so we didn't go into the detail of computing the rates because a lot of things are very uncertain, like the binary fraction at those low metallicities. So we do not make any calculations on that, sadly. Yeah.
Johanna Müller-Horn, I had a question for Casey. You said that the one detection of the isolated black hole was consistent with the upper limit of 10 to the 8 black holes in the Milky Way, but in the end you mentioned that there are several new candidates that you're following up with KEC data. So is finding several more still consistent, or would you revise the limit then?
Yeah, so I think it's still in progress, but it would depend on the exact time scales, and so there's also additional non-detections. And so the total sample size is now approaching 20 objects, and so, in 1 or 2 years, I think, so I'm not really answering your question, but in 1 or 2 years we'll have a better answer, I think, in order to figure out what those constraints are.
Okay, let me get back to Puglia. I didn't want to ask too many at the same time for you. I tried to scan in your paper what you do for how much angular momentum the black hole is accreting, but maybe you do different things. At some point, I find the reference to Bardeen model for thin disk accretion. I wonder in how many of the cases that you're thinking of is this thin disk angular momentum actually relevant, in particular if you talk about much higher accretion rate and there's a thick torus or even a black hole inside a star. I'm not an expert here, but I had long discussions with Ramesh Narayan, who certainly is, who was telling me that the motions would be so randomized that the maximum spin you would get would be at best 0.3 or so. Yeah. I don't know what the status is there and what you assume.
Yeah, that's a great point. So the accretion disk geometry depends on how the disruption radius. If you disrupt the star within a tidal disruption radius, you may form a disk, and if it is especially low mass star, but if you have a direct collision between the black hole and star, and if the black hole is less massive, you can sink the black hole to the star center, then you have a completely different scenario.
But even if you form a disk, do you really form the thin disk that is needed?
No, it's still not a thin disk. Yeah, our hydro simulations show that it's kind of like spherical torus. It's not like a thin disk. It's more like thick spherical torus.
So, are you going to ask? Okay.
Sorry, I had a question about the subsolar mass neutron star scenario. Can you remind us what the delay time is you expect between the collapsar and the merger is? And if so, given that we may, of course, not see the long GRB because it would be off axis, but shouldn't we see a type 1c broadline supernova? And given the distances at which LIGO is sensitive to these things, would we have expected to see something like that if this was if there was a precursor, or, well, actually post-cursor really, because the 1CBL rise time is longer than the delay time. Should we be looking for something there?
Yeah, so I think if you have a scenario like that, the precursor will be something like a type 1b, type 1c broadline supernova that's connected with a collapsar scenario. And then, there are two scenarios for the gravitational wave event. If you have if you have multiple neutron stars, the neutron stars themselves can merge among each other. And then there's one, if you form one neutron star, or the merged component of binary neutron stars can merge when they inspiral toward the central black hole. And then the time scale for GRBs may be, just a few seconds, and then or 10 seconds. And the gravitational wave inspiral time scale from the typical gravitational instability radii towards the center is on the order of 1,000 seconds. So yeah, you would expect some delay if you have some multi-messenger events that happen at the gravitational instability radii, and if you want to follow up, and that's going to be the delay time scale towards the second episode of gravitational waves.
Right, the 1CBL has a much longer rise time than 1,000 seconds, so it's actually, in fact, it's post-cursor, but you should, by now, shouldn't we have seen something?
You mean specially pointed out towards the event last week or something? Yeah, we haven't seen anything. Yeah. So I think we're good.
Fair point.
Yeah, but that itself, I'm not sure, in our scenario, there's, one possible gravitational wave event from binary neutron stars and another one from, the inspiral. So I'm not sure, which one of these can be more associated with a precursor or postcursor.
Okay, do we have one last question before lunch? Is everybody hungry? Okay, one last question.
No, sorry, it is Sylvia? Okay. For a non-expert, I'm just trying to understand. So it looks like that the rotation of a core, of course, is playing a very big role in being able to form these massive black holes, right? So do you have binary stars that are slightly detached from each other but still tidally interacting, where you can have rotation, where you populate not just the absolute upper part of the mass gap, but you have more broad distribution of heavier black hole masses from that tidal locking, where you don't have this very close system you looked at, or
so do you make the difference between over contact and
that is probably what I mean.
So in my sample, sorry. So I think in other CHE grids at the lower masses, most of them are actually over contact. But at this ones, like at this high masses, because already the stars are like 80-90% convective, it's easier to sustain this chemically homogeneous evolution. And only a small fraction of my models are actually in over contact. The other ones are detached systems. I mean, still close, but yeah. So you're wondering if tides can.
So the detached systems. I was trying to understand it.
Yep, here. It's fine.
Oh, so I was just trying to understand if the detached systems could also create such a high, a relatively high spin of the core that you will be able to form heavier black holes that are not as heavy as here, but maybe 60 or 80 or something. Like if you have a mass spectrum of how these stars that have spin of the cores, that like how they populate the upper mass gap, and not just this extreme event.
Yeah.
Well, does it make sense? My question is just trying to.
No, yeah, I think I don't know like, yeah.
Maybe it doesn't.
Yeah, maybe it's not enough.
I said I was just not expert.
Sylvia would be great in giving you a distribution of progenitors someday later, because this was a rapid paper over the summer. But the question is, how does that collapse? And this is GRMHD simulations with magnetic field that you need to treat well. And I don't think, it's a great paper, but Gottlieb's paper has 5 assumptions for the magnetic fields and makes every spin and mass across the plane. So I don't think it's us that's the problem here. But I think, so you're so optimistic. I think it's too hard.
All right, this is really rich discussion for lunch. I hope you reach out to all of them again. And let's thank our speakers for this session. And we're adjourning for lunch until 2 o'clock.